Welcome everyone. I'm excited to present you causal effect inference for structured treatments, which is joint work with Eugen, Ji, Matt, and Ricardo. We will start with some motivation behind this work and then jump straight into our main contribution, the generalized Robinson decomposition. Eugen will then present a quasi-oracle convergence rate of this decomposition, and I will conclude with a practical learning algorithm called structured intervention networks. Lastly, we will have a look at some experiments and then summarize the contributions. Let's start. Imagine you were at a party, had a drink, and felt quite bad afterwards. Now imagine in a different world that is not observed, where you had drunk milk, you would continue being happy. Similarly, if you had drunk coffee, you would perhaps feel even more alive. Now, this effect of changing the treatment on the expected outcome given some characteristics of an individual or group is what we call the conditional average treatment effect, or CATE in short. While these CATEs have been well studied in previous years, in this work, we will look at estimating them with structured treatments that have explicit features. For example, a molecular graph, an image, or a text embedding. As I already hinted at, a common problem we face when estimating these effects is we only observe one outcome for each covariance and treatment pair. Now, if you were to reason about the effect of a drink on your well-being that you haven't tried before, you might probably recall what happened to similar friends of yours. For example, your old flatmate from college who was a bit groggy after waking up and felt much more alive after drinking her first coffee in the morning. Or perhaps your nerdy work colleague who enjoyed drinking milk during work and pretty much stayed the same. In causal effect estimation, we have access to a data set with multiple individuals or groups and then want to generalize causal effects across covariates. To make this more formal, we assume this causal graph, a data set containing realizations of these random variables. We make the overlap and unconfounded assumptions that are explained in the paper, and we can now turn the CATE estimand into a statistical estimand only consisting of conditional expectations. A question that naturally arises is, why can't we simply learn a model of this conditional expectation and then simply subtract two predictions? Well, technically speaking, yes, we could do that, but we would like to follow Vladimir Vapnik's recommendation. When solving a problem of interest, do not solve a more general problem as an intermediate step. Try to get the answer that you really need, but not a more general one. Let's look more closely why targeting the effect directly helps. One reason can be that the effect exhibits a simpler structure than the outcome surface. For example, assuming a binary treatment setup, we may have very non-smooth regressors for rarely treated covariates. However, the true CATE might be almost linear across the covariates. So targeting the CATE can be much easier. Another quite related reason is that we can reduce regularization bias. Formalizing this requires quite some machinery, so we will focus on a quite simple example here. Imagine you had covariates and treatments with much different dimensionalities. X might be a high-dimensional image, and T is a binary indicator variable. Now, if you were to regress the outcome, you would extract features of the image and then concatenate them with the treatment. However, this can regularize the model towards ignoring the lower dimensional treatment variable, and therefore a causal effect of 0. Of course, there has been done a lot of work on CATE estimation already. However, most of these only deal with binary or scalar continuous treatments. You might wonder, why is dealing with structured treatments interesting in the first place? Let us quickly look at 3 reasons. Firstly, data efficiency. The more we know, for example, about the ingredients of a cocktail, as long as that information is predictive, the better we can do inference. Secondly, we might work in a setting with many treatments, possibly infinitely many. Looking at previous neural network-based CATE estimators, we see that they often assign a separate prediction head for each treatment level. This, of course, does not scale well in the number of treatment options. So inferring the effect of, for example, a variety of different cocktails might be very difficult with these approaches. Lastly, we might want to generalize to unseen treatments at inference time. Imagine you had a barkeeper robot running with some AI that is supposed to mix a novel cocktail for you. If this novel cocktail has not been observed before, it gets hard for most previous approaches to infer any causal effects since they do not take treatment features into account. All these considerations lead us to two issues. One, how can we represent the CATE with structured treatments? Well, the goal is to take covariates and the treatment features into account. Secondly, how can we learn the relevant feature maps of the effect such that we yield a trainable objective designed to target the CATE? For solving both these issues, we propose the generalized Robinson decomposition. Let's take some inspiration from dealing with the binary treatment case. The Robinson decomposition, as used in the R learner, is one method for that. It allows us to construct a learnable objective of the binary CATE. First, we define the propensity score E of x, then the conditional mean outcome M of x. We call E and M the nuisance components. And now we can do some algebraic steps that yield these objectives, including estimators for the nuisance components M and E. In our work, we generalize this to structured treatments. First, we make the product effect assumption, meaning that we can decompose the outcome into a product term of two functionals, G and H, on the covariates and treatment, respectively. We can prove that this assumption has an universality property, meaning that as we let the dimensions of the functionals G and H grow, we can approximate any bounded continuous function involving the product space. This lets us rewrite the CATE in a form that takes both covariates and treatment features into account, thereby resolving the first issue. However, this still does not help us doing inference. To do that, we first define propensity features as the conditional expectation of h of t given x. We recall the definition of the conditional mean outcome, which we can now rewrite in form of the propensity features. Following the same algebraic steps as in the binary case, we yield the generalized Robinson decomposition, targeting the causal effect, which lets us derive a directly trainable objective. I will now hand over to Yu-Chen, who will describe the decomposition's quasi-oracle convergence rate.
Hi. So what is the power of our decomposition? How do we know in principle that it is better than doing a vanilla regression? In this work, we prove that under finite feature representation of the covariates and the treatments, i.e. the response function is a linear combination of the cross features on the treatments and covariates. Our decomposition allows the estimate of the response function to converge to the ground truth response function with almost root n rate. We show that this is achieved while we allow the nuisance functions to converge at only n to the 1/4 rate. In particular, our result only assumes the overlap condition on the features of x and t, which is a more relaxed condition in the settings where x and t are themselves high-dimensional variables. Our result is significant because, as discussed in, for example, the double machine learning paper by Chernochukov in 2018, the convergence rate of the target function and nuisance functions cannot be faster than root n. Usually, the convergence rate of the target function is capped by the rate of nuisance functions, which is often significantly slower than root n. Our work thus shows that under our formulation, the rate of learning the target function is still almost root n, even though that of the nuisance function is significantly slower.
Thank you, Yu-Chen. As a recap, we got this trainable objective over here, where we fixed the functional over the treatments. Now, how can we turn this into a practical learning algorithm? We propose a two-stage training procedure. In the first stage, we learn only the conditional mean outcome model based on a least squares objective. In the second stage, we alternate between optimizing the covariates and treatment feature maps and the propensity features model. In the first sub-step, we only optimize the feature maps and freeze the other models. In the second sub-step, we only optimize the propensity features model. We can split up the two stages, resulting in an algorithm as shown here. One thing to notice is that we have a higher number of update steps for the first sub-step of stage 2, since we empirically observe that this leads to much better performance. Of course, we also include a 280-character PyTorch-like implementation in the paper. So far, this talk has been fairly theoretical, so let's look at some empirical results. We use two semi-synthetic datasets involving graph treatments, which we denote by the SW and TCGA. The tasks are to predict within sample and out sample CATEs. We compare against graphite, a method designed for graph interventions, as well as vanilla regression with 1, taking treatment features into account, denoted by GNN, and 2, without using these features, denoted as the categorical treatment variable model, or in short, CATE. Lastly, we also have a baseline that predicts 0 causal effect all the time. As an evaluation metric, we use the unweighted and weighted expected precision in estimation of heterogeneous effects. Let's look at some results. On the x-axis, we see the number of considered treatments increasing, where the treatments are chosen by the true assignment policy. On the y-axis, we see the unweighted p-he averaged over all covariates and treatment combinations. We can see that SYN performs significantly better than the baselines in both tasks for the SW dataset. For the TCGA dataset, we also see that SYN performs best. Surprisingly, we see that the second strongest method is the 0 baseline, illustrating an evident case of regularization bias. For the weighted p-he, where we use the true propensities as weights, we here show results where we fix the number of considered treatments for each covariate vector to 6. In the paper, we also include the results for other values of k. SYN, again, outperforms the other approaches consistently. Now let us summarize. We dealt with the estimation of CATEs, where we considered structured treatments, such as molecular graphs. We considered this type of treatment mainly for 3 practical reasons: data efficiency, many treatment settings, and generalization to unseen treatments. Our proposed solution is the generalized Robinson decomposition. Thank you so much for listening to this presentation.